Google just published a compression algorithm that cuts AI memory usage by 6 times with zero accuracy loss. If that holds up in production, it rewrites the cost structure of every company running large language models. Here is exactly what TurboQuant does, what it does not do, and what you should be thinking about right now. On March 24th, Google Research dropped a paper called TurboQuant. It will be presented at ICLR 2026 next month. The internet immediately started calling it the real-life Pied Piper, after the fictional compression startup from HBO's Silicon Valley. The comparison is fun, but the substance underneath is serious. Here is the problem TurboQuant solves, in plain terms. When a large language model has a conversation with you, it needs to remember everything said earlier in that conversation. It stores that memory in something called the key value cache. Think of it as a high-speed notebook the model scribbles in so it does not have to reread the entire conversation every time it generates a new word. The longer the conversation, the bigger that notebook gets, and the more expensive GPU memory it consumes. That memory is the single biggest bottleneck in long-context inference today. TurboQuant compresses that notebook from 16 bits per value down to as few as 3. It does this through 2 techniques working together. The first is called polar quant. Instead of recording each value along standard X, Y, Z axes, polar quant converts them into a radius and a set of angles, like switching from street grid directions to compass bearing and distance. Because the angles cluster in predictable patterns, you skip the expensive normalization step that other compression methods need, the step that quietly eats into your savings by storing extra metadata. The second technique is QJL, based on the Johnson-Lindenstrauss transform, which mops up the residual error from the first stage using just a single sign bit per dimension. The combined result, most of the compression budget captures the actual meaning of the data, a tiny bit handles error correction, and nothing is wasted on bookkeeping overhead. Google tested this across 5 standard benchmarks, including Longbench, Needle in a Haystack, and Zero Scrolls using Gemma, Mistral, and Llama models. At 3 bits per value, TurboQuant matched or beat Kiwi, the previous state-of-the-art cache compression method. On Needle in a Haystack tasks, where the model has to find one specific fact buried in a massive wall of text, TurboQuant scored perfectly while compressing the cache 6-fold. At 4-bit precision on NVIDIA H100 GPUs, it delivered up to an 8 times speedup in attention computation compared to uncompressed 32-bit baselines. And here is a detail that matters enormously for adoption. TurboQuant requires no retraining, no fine-tuning, no access to original training data. You drop it into an existing inference pipeline as a compression layer. Within hours of publication, developers were already porting it to Apple Silicon, and one developer tested it on a 35 billion parameter model and reported exact matches against full precision output. So, what does this actually change for you? Let me walk through 3 concrete scenarios. First, if you run AI inference at scale, either directly or through a cloud provider, a 6 times reduction in KV cache memory means you can serve dramatically more concurrent users on the same hardware, or you can handle much longer context windows without upgrading your GPU fleet. Either way, your cost per token drops materially. Second, if you are building AI-powered products on mid-size open-source models, TurboQuant could let you run models locally on consumer hardware that previously required server-grade GPUs. A model that needed 64 gigabytes of working memory for a long conversation might now fit in 10. That opens up edge deployment and on-device AI in ways that were not practical last week. Third, and this is easy to overlook, TurboQuant also applies to vector search. It compressed vector databases while outperforming established methods like product quantization on retrieval accuracy, and it completed indexing in under a millisecond where competing methods took seconds to over an hour. If you run semantic search or recommendation systems, that is a direct cost and speed improvement. Now, let me be clear about the limits, because they are real and important. TurboQuant compresses inference memory, not model weights. Loading a massive model still requires the same storage, and it does not touch training. The enormous RAM demands of pre-training and fine-tuning are completely unaffected. Cloudflare CEO Matthew Prince called this Google's DeepSeek moment, but that comparison is premature. DeepSeek was a deployed system that demonstrated efficiency gains in production. TurboQuant is still a lab result. It has been tested on research benchmarks, not on messy real-world serving with irregular batch sizes, diverse prompts, custom attention variants, and strict latency requirements. There are also open questions about robustness across different architectures. mixture of experts models, speculative decoding, retrieval augmented generation setups, these may all interact differently with compressed caches. Google has not disclosed whether TurboQuant will be open-sourced or kept proprietary, and they have not announced integration timelines for Gemini or Google Cloud. Memory stocks like Micron, Western Digital, and Seagate dropped on the news, but as one analyst noted, KV cache compression may be approaching its theoretical limits. The remaining efficiency gains beyond this point will likely require a fundamentally different approach. Here is what I would do in the next 30 days if this is relevant to your work. 1. Read the actual Google Research blog post and the paper when it drops at ICLR. Understand the difference between KV cache compression and weight compression so you can evaluate claims accurately. 2. If you are running inference workloads, benchmark your current KV cache memory consumption across your most common context lengths. You need a baseline before you can estimate what TurboQuant class techniques could save you. 3. If you are on a smaller team running open source models locally, watch the community ports closely. Developers are already adapting this for consumer hardware. Test it on your specific models and use cases as soon as a stable implementation is available. 4. Do not make infrastructure purchasing decisions based on this paper alone. It is a lab result. Wait for independent production benchmarks and Google's deployment timeline before reallocating capital. 5. Brief your engineering and finance teams on what inference time compression means for your AI cost model. Even if TurboQuant itself takes months to reach production, the direction is clear. Inference is getting cheaper, and your unit economics projections should reflect that trajectory. The bottom line is this: TurboQuant is the most credible inference efficiency breakthrough we have seen this year, mathematically grounded, benchmarked across multiple model families, and requiring zero retraining. But it is not in production yet, and the gap between a perfect lab score and reliable real-world deployment is exactly where most breakthroughs quietly die. Watch this one closely. If you want to stay ahead of the AI developments that actually matter for business, subscribe to AI Blueprint. We break down what is real, what is hype, and what you should do about it.